Before I start this video, I'd like to give big thanks to Wolfie6020 for delivering the gift as he promised. The gift was $100 for joining the Equinox contests. I hope this is encouragement for people to join his contests and share their views and experiments. So again, thanks Wolfie. Now to the video. Today I'll answer a question that flat earthers never attempted to answer. What are the shape and distance for Earth and stars or the Sun that fulfills the observation of changing elevation angle 1 degree every 111 kilometers? Flat earthers object on Eratosthenes' experiment for a reason that he presumed the Sun's distance to be almost infinity, and so concluded the Earth's shape to be a sphere. Well, side note, Eratosthenes' experiment was to conclude the Earth's size, not its shape. The shape was already concluded long before him. But anyway, here's an example that demonstrates why flat earthers criticize the star's elevation angles, a method to determine the shape of the Earth. If we want to know the speed of a vehicle, we can do that by dividing the distance by time. We want the speed, and we have two inputs, that's the distance and time. So we can get the third one. Now, for using elevation angles to determine the shape of the Earth, now flat earthers see here two question marks: the shape of the Earth that we want to conclude, and the distance to the stars that we don't know. On the globe, the distances are virtually infinity. But anyway, I'll show a method where we can test many or various altitudes for a star and see what elevation angles it will be produced when we move 111 kilometers. So I started by this diagram and chose a star at a unknown altitude, and we move equal steps. That's supposed to be 111 kilometers, and those steps should result in a 1 degree rate of change for elevation angle. And just in case, I put some calculations for any variation in vertical change for each step of those 111 kilometers. And any vertical change will be combined with a slight change in horizontal distance. So in order to do that, I made this spreadsheet with these inputs, and eventually it will plot out the surface that will fulfill the requirements of change 1 degree of elevation angle every 111 kilometer 0.24. So I found out that the proper distance to make that change is 6,360. Now if we change that into just 6,000, now you see that some change happened earlier than the first one. So if we go back to, let's say, 6,500, again there's a change that happens earlier, and that change is not really big as we see here. So back again to, this is the best reading. This here, the observed elevation angle that we can observe practically, So here's 1 degree difference after 660 kilometers. So this is the observed angle, and this is the surface tilt. There should be some tilt for the surface in order to make this elevation angle change from 84.01 into 84. And that tilt, as I show in this picture, could be upward, could be downward, it doesn't matter. That vertical step and horizontal step here. So this is the X and Y, and as you see, the X is almost the same because the change or the tilt is very tiny. And for Y, this is 111 meters after 1000 kilometer. Of course, if you go to Earth curvature calculator, you'll find a huge result for this distance comparing to the minus 111 meters. And then I have the total X and then the total Y, and these are the numbers that I plotted on the graph. So let's see the graph. This is it here. So this is the star at 6,360, and this is the first point where we measured the elevation angle to be 90. Then as we move here, the surface must tilt down in order to fulfill the angle for each step. So what we'll do now, we try to change the distance and see what's going to happen. We pull this to the left. So let's pick 5,000. That's kind of creepy. Okay, let's say 500. Okay, it's better on the middle. And notice that this is a 1000 kilometer, and it's not the scale here, so I think we should go back to the first number and put the X and Y to scale. So this is 1000, this should be a square. So we stretch it. So now it's a square, but we still see that after 4,000 kilometers, it start to curve down. Down to 2,000 kilometers when it's around 9,500. So let's get back and try another number. Alright, still the same problem. Let's try 4,500. So these are 90 points here, and as you see, in order for each one to measure the elevation angle, the surface must go up and go down. And so let's test the last point. We'll make a line here from the star to the last point, and I think you can see that indeed it is a zero. It's a zero at 10,000 kilometers. That's what we observe in reality. That's on the equator, the elevation angle of the polar star is zero, if you can see it. So I think there's no point going down anymore, but let's just see what's going to happen. Say 3,500. It's getting more creepy. 3,000. So we shouldn't go down anymore, we should go up. Let's try 6,360. That's the first one, which is the best one so far. So let's go higher, say 6,500. It doesn't look good. 7,000. It's going worse for the flat earth. Let's say 10,000. So again, a reminder, These plots are 90 points. The distance between each point is 111 kilometer, 0.34, and they are in this arrangement showing the surface that guarantees that the measurement of the elevation angle to that point decreases by 1 degree. Okay, so let's go higher. Let's say 15,000 kilometers. The star is out of the chart, but anyway, that is the shape from 0 to 10,000 kilometers. Of course, here it's not 10,000 because this is curving down. So let's go higher because I lost hope on any flat Earth model that matches the observation, but let's go experimental. So 20,000. It's curving more down. Looks like it's going to be a ball. So let's say 30,000. Okay, let's try 100,000. So again, if a star that is 100,000 away from a surface that measured the elevation angle to be 90 degrees, and we moved 111.24 kilometers steps, the change of elevation angle will be 1 degree for each step. It looks like a ball, but it's not exactly a ball if the star is at this distance. Let's try the moon, which I think 400,000. So this is how it would look like. Let's try 1 million. 1 million kilometers. A star at 1 million kilometers would produce this result. But oh damn me, I forgot to scale the charts. So let's go back to the moon distance and scale the chart. Now these are squares, almost squares. Yeah, okay, so let's try 1 million. I think it's clear that this is a part of a ball. Let's try 5 million kilometers. Well, the change, as you see, is very slight. But as you see, if I adjust this to be squares, yeah, and you can check if these are perfect squares or not. Maybe I stretch a little bit. So it's obvious here that this is a quarter of a ball, and the drop here is 6,000, less than a half, 6,300, 400, something like that, which is the radius of the Earth, and the horizontal is also the same. So at 5 million kilometer, a star would produce the observation that we have on Earth. The sun doesn't have to be 150 million kilometers. Well, let's try 1 million only. I didn't notice any change. Oh my god. Let's try back again, forward again. Change is almost insignificant for the eyes. So let's try 500,000. Even at 500,000 distance of a star or celestial object, observations will guarantee a change of elevation angle of 1 degree on this shape. It's not flat. It cannot be flat. Thank you all for watching.
Is there no one else? Is there no one else?